Imagine you're sitting in a self-driving car, just, you know, cruising down a highway at 70 miles per hour. It's dusk.
Yeah, the lighting is getting tricky.
Exactly. And out of nowhere, a pedestrian steps off the curb up ahead. Now, your human brain processes that visual information, recognizes the danger, and hits the brakes in a fraction of a second.
Right. It's virtually instantaneous for us.
But just a few years ago, if you handed that exact same visual scene to the world's most advanced artificial intelligence, it would have taken an agonizing 47 seconds just to locate the pedestrian in the frame.
47 seconds. I mean, it's terrifying to even think about that kind of latency.
By the time the computer figured out where the person was, the car would be halfway down the next block.
Yeah, we totally take instant machine perception for granted now. But that gap between seeing an image and actually, understanding the spatial reality of it, that was an absolute wall for researchers.
And that's exactly the journey we're taking you on for this deep dive. Settle in, because we have a fascinating stack of software engineering curriculum notes in front of us, and our mission tonight is to trace one of the most blistering optimizations in modern computer science.
It really is an incredible story.
We are tracking the evolution of object detection. In just 8 short years, engineers took that 47-second delay and accelerated it by over 7,000 times,
Which is just wild.
hitting 155 frames per second.
To really grasp the magnitude of that leap, we kind of have to pull apart a fundamental distinction in computer vision. Because for the longest time, the holy grail was just basic classification.
Right.
You feed an image of a street into a neural network and it spits out a label like street scene or dog or car.
Which is, it's an impressive math trick.
Yeah.
But it's not how you or I actually experience the world.
No, not at all.
When you look at that street, your brain doesn't just print out a generic text tag. You instantly isolate the red sedan turning left. You track the cyclist weaving through traffic.
You spot the yellow traffic light.
Exactly. You're simultaneously identifying what everything is and mapping exactly where it is in three-dimensional space. And you do all of that without knowing in advance how many things you're supposed to be looking for.
Right, because classification just asks, what is this? Object detection demands to know where exactly is everything.
It's a much harder question.
Oh, absolutely. It forces the machine to draw precise bounding boxes around every distinct entity in a really chaotic environment. And doing both of those tasks at the exact same time is a computational nightmare.
So how do you solve a nightmare? Well, in the beginning, you just throw an absurd amount of raw compute at it.
As we always do in software.
Right. Let's travel back to 2014. A researcher named Bras Gershik and his team introduced an architecture called RCNN. That stands for Regions with Convolutional Neural Network Features.
Yeah, and the mechanism they used to actually find those bounding boxes was just incredibly crude.
How crude are we talking?
Well, the underlying logic of RCNN was essentially organized guessing. It didn't even use AI to find the locations. It used a classical, old-school computer vision algorithm called selective search.
Okay, let's unpack this. What does selective search actually do?
Think of selective search as a very basic filter. It just groups pixels together if they share similar colors or textures. So it sweeps over the image and says, here's a brown blob, maybe that's something. Here's a shiny silver blob, maybe that's something.
And it generates around 2,000 of those guesses or proposals for every single image.
2,000 guesses. And here is where the computational torture begins. For every single one of those 2,000 random blobs, the RCNN system would physically crop that piece of the image out.
Oh, man.
Yeah, it would warp it to a standard square size and then run a full convolutional neural network forward pass on it.
As someone who writes software, just hearing that makes my CPU hurt. I mean, a convolutional neural network, a CNN, is a massive web of matrix multiplications.
It takes huge amounts of memory bandwidth.
Running a heavy CNN forward pass 2,000 times per frame. That is an absolute architectural bottleneck.
It really is.
It's like a detective walking into a massive warehouse crime scene, pulling out a tiny magnifying glass, getting on their hands and knees, looking at a 2-inch square of the floor, standing up, wiping their memory completely blank, and then moving to the next 2-inch square. 2,000 times.
That is the perfect analogy. It was wildly inefficient. And that's exactly why it took 47 seconds to process a single image, even on a top-tier GPU at the time.
But we have to give it credit, right? It actually worked.
Oh, it shattered the previous accuracy benchmarks. It proved to the world that deep learning could definitively solve object detection.
Even if the implementation was painfully slow.
Right. But obviously, that 2,000 pass bottleneck was totally unsustainable.
So you've got this incredibly powerful neural net sitting there doing repetitive labor, just choking on memory allocation. How do they bridge that gap and share the workload?
The breakthrough came a year later in 2015 with an architecture aptly named FastRCNN.
Fast RCNN.
Yeah, and the engineering insight here was brilliant because it completely inverted the workflow. Instead of running the massive neural network 2,000 times on tiny cropped regions, they decided to run the neural network exactly once on the entire uncropped image.
Ah, so you pass the whole image through to create one master feature map.
A master feature map, exactly. You run the image through the CNN layers, which translates the raw pixels into a dense grid of semantic features. Then, you still use that old selective search algorithm to generate your 2,000 guesses.
But you're not cropping the original image anymore.
Right. Instead of cropping the heavy, high-resolution original image, you use a clever math operation called ROI pooling. Region of interest pooling. You take the coordinates of the guess, map them directly onto that pre-calculated master feature map, and just extract the data you need.
Okay, so it's like a photographer setting up a tripod, taking one massive, ultra-high-resolution panoramic photo of a valley, and then going back to the studio to just crop out the interesting birds and trees later. That is vastly cheaper than running around the valley taking 2,000 separate macro photographs.
The shared computation was a total revelation. By running the heavy math once, the processing time plummeted from 47 seconds per image down to just 2 seconds.
A huge win. But, let's go back to our self-driving car scenario. 2 seconds is still an eternity.
Oh, yeah.
If the car needs 2 seconds to realize there's a pedestrian in the crosswalk, you're still going to crash.
Right, because the neural network wasn't the anchor anymore.
The anchor was the classical algorithm,
Yes,
wasn't it?
exactly. Selective search ran on the CPU. It couldn't be accelerated by the massive parallel processing of GPUs in the same way the neural network could. So you had this lightning-fast AI waiting around for a clunky 1990s color sorting algorithm to tell it where to look.
So the classical algorithm gets thrown in the trash.
It had to be. Later in 2015, the team released Faster RCNN. They made the entire pipeline end-to-end depth learning by introducing the Region Proposal Network, or RPN.
So they replaced selective search with another neural network.
Yes, they trained a small secondary neural network to slide across that master feature map and actually predict where objects were likely to be.
And this is where the curriculum notes highlight a concept that totally revolutionized the field. Anchor boxes.
Oh, this is a crucial mechanism.
Right.
The model doesn't just hallucinate bounding boxes out of thin air. Real-world objects generally conform to predictable aspect ratios, A standing pedestrian is tall and narrow.
A parked car is wide and short.
The stop sign is roughly square. So at every single location on the feature map grid, the system drops 9 predefined reference boxes. You have 3 scales, small, medium, large cross, with 3 aspect ratios, tall, square, wide.
I love this concept. Rather than asking the network to guess coordinates from scratch, you give it a template and ask it to make adjustments.
Exactly.
It says, okay, take that medium-sized tall anchor box, stretch the height by 10%, and shift it 2 pixels to the left. It's like a tailor making a custom suit.
That's a great way to look at it.
Instead of cutting raw fabric from a massive spool, the tailor pulls a standard medium slim fit jacket off the rack and just takes in the seams a bit to fit you perfectly. It requires vastly less mathematical heavy lifting to adjust a prior than to generate a shape from absolutely nothing.
That adjustment process is incredibly efficient. But as you scale it up across the whole image, it introduces a very messy reality.
Yeah, I was just looking at the system design here, and it seems like there's a glaring logical flaw.
Oh, what do you see?
Well, if you are throwing 9 anchor boxes at every single point on a dense grid, and the network is tweaking all of them to fit objects, wouldn't you just end up with an absolute blizzard of overlapping rectangles around a single car?
You would.
You'd have 50 different boxes all shouting, "I found the car! I found the car!"
You've zeroed in on the exact headache every 2-stage detection system creates. It generates a massive redundant mess. The network is essentially overeager.
So how do you clean that up?
To clean it up, engineers rely on a ruthless post-processing algorithm called non-maximum suppression, or NMS.
Okay, but how does the NMS algorithm actually know which box is the real one and which ones are just the overeager duplicates?
It calculates a metric called intersection over union, or IOU. It's just a simple fraction. You take the overlapping area between two bounding boxes and divide it by the total area both boxes cover combined.
Okay, so if the box is perfectly aligned, the IOU is 1.0.
Exactly. And if they don't touch at all, it's 0. So NMS runs through the mess and says if any two boxes overlap by more than 50%, they are probably looking at the same object.
Makes sense.
It checks their confidence scores. Let's say one box is 98% confident it's a car, and the overlapping box is only 85% confident. NMS keeps the 98% box and permanently deletes the 85% box.
So it cascades through the image, sorting by confidence and suppressing the overlaps until only one clean box remains per object.
Right, it just prunes the weeds.
But hold on, what if two objects in the real world actually DO overlap by more than 50%? Think about a dense crowd at a concert where people are standing shoulder to shoulder, front to back.
Ah, that is the famous failure mode of non-maximum suppression. In a dense crowd, NMS is totally blind to context.
It just sees the overlap.
Right. It looks at the bounding box of a person in the front row, sees the bounding box of the person standing directly behind them, sees the heavy overlap, and just deletes the person in the back.
Oh, wow.
Yeah.
It literally erases valid detections because its math dictates that two things can't occupy the same spatial area.
Yes. Engineers spent years developing soft NMS tweaks to try and fix that exact crowd problem.
Even with those tweaks, faster RCNN gets us to about 5 frames per second. It's much faster, but 5 frames per second is choppy video. It's not true, fluid real time.
No, it's not.
It seems like the two-stage architecture. First, propose a region, then classify it, hit a physical speed limit.
It did. The two stages were inherently bottlenecked. To shatter that limit, someone had to throw out the entire paradigm and ask a radical question. What if we don't propose regions at all?
What if we just do it all at exactly the same time? Here's where it gets really interesting. In 2016, Joseph Redman and his team drop YOLO. You only look once. And they completely reframed the engineering challenge. They stopped treating object detection as a multi-stage search, and they turned it into a single regression problem.
That shift from classification to regression is profound, and we really need to unpack what that actually means computationally.
Let's do it. Because when we talk about classification, the network is basically answering a multiple-choice question.
Right.
Is this a dog, a cat, or a car? It spits out probabilities for discrete categories.
Correct.
But a regression problem is entirely different. Regression is about predicting continuous numbers. Instead of picking from a list of labels, the network is solving an ongoing math equation to output exact continuous x and y coordinates, plus the height and width of the box.
Exactly. YOLO takes the entire input image and lays a rigid grid over it. The original used a 7x7 grid, and instead of searching the image, it just forces every single one of those 49 grid cells to simultaneously run that regression math.
So in one single forward pass, every cell predicts bounding box coordinates, confidence scores, and class probabilities.
All at once.
If faster RCNN is like a detective carefully walking into a room and searching it corner by corner, YOLO is like standing in the doorway, taking one sweeping glance, and instantly shouting out the coordinates of every object in the room.
That's beautifully put. And because it truly only looks once, the speed is staggering. The original YOLO hit 45 frames per second.
And the streamlined version, fast YOLO, hit 155 frames per second.
For the first time in history, deep learning had achieved true, fluid, real-time object detection.
But there is no free lunch in software architecture, is there?
Yeah.
You don't get a speed up of that magnitude without paying a steep price somewhere else.
The price YOLO paid was accuracy, specifically with small objects or objects clustered closely together. And the reason lies in the rigid math of that 7x7 grid.
Let's break down the mechanism there. Why does the grid fail with small objects?
Because of hard-coded limitations. In the original YOLO architecture, each grid cell was mathematically constrained to predict a maximum of 2 bounding boxes, and it could only assign one class label to that cell.
Okay, so imagine an image of a flock of 10 small birds flying tightly together.
Right. That entire flock might fall into a single grid cell, but the network is physically incapable of outputting 10 boxes. The architecture only has the mathematical slots to output 2.
It literally blinds itself to the rest of the flock.
Exactly.
Wait, if the limitation is just the size of the grid, wouldn't the obvious software fix be to just make the grid way smaller? Like, why not use a 100 by 100 grid instead of 7 by 7? Wouldn't that solve the flock of birds problem?
You'd think so, but increasing the grid density that aggressively explodes the computational cost, you completely lose the real-time speed advantage that made YOLO revolutionary in the first place.
Ah, I see.
Plus, a tiny grid cell doesn't have enough spatial context to detect a massive object, like a bus that takes up half the screen.
You need different perspectives.
Which is how the industry found a highly elegant middle ground later that same year with a model called SSD, or single-shot multi-box detector.
SSD kept YOLO's blazing fast single pass idea, right?
It did, but it made predictions by pulling features from multiple different layers deep inside the neural network.
Because early layers in a neural network capture high-resolution, fine-grained details, edges, and textures, while the deeper layers capture the broad, low-resolution semantic meaning of the whole image.
That's the exact mechanism. SSD attached prediction heads to multiple layers simultaneously. It was like giving the model both a wide-angle lens to capture the large objects from the deep layers and a high-powered zoom lens to capture the tiny objects from the early layer.
So it achieves speeds very close to YOLO, but solved that frustrating blindness to small, clustered objects.
Right.
And that single-shot philosophy really became the bedrock of the industry. The notes show engineers fiercely iterating on the YOLO concept for years. YOLO version 2, version 3, all the way up to version 8 and beyond.
They added the anchor boxes back in. They bolted on feature pyramid networks. They used crazy mosaic data augmentations.
It was a blizzard of training tricks that turned a wild academic idea into the reliable workhorse of industrial AI.
It is the classic software engineering life cycle. You have the messy, revolutionary breakthrough, followed by a decade of relentless, incremental optimization that hardens a wild idea into invisible infrastructure.
But just when you think the architecture is permanently settled, the industry throws a massive curveball. Because in 2020, Facebook AI released an architecture called DTR Detection Transformer.
Oh, yes.
And they just took a bulldozer to all the established rules.
They really did. DETR strips away almost all the handcrafted hacks we've discussed today. It rips out the anchor boxes, it eliminates the region proposal networks, it completely removes non-maximum suppression.
Wow.
It replaces that entire fragile pipeline with a single transformer architecture.
Transformers, the exact same underlying architecture that powers the massive language models generating text today.
The very same. Now, DETR still uses a standard CNN at the very beginning to extract basic features, but then it feeds those features into a transformer. And to understand how it works, we have to look at a mechanism called cross-attention.
Okay, let's talk about cross-attention.
In a language model, attention lets the word bang know if it's near a river or a vault. In DETR, cross-attention lets the model look at the entire image context at once. A pixel in the top left corner can mathematically communicate with a pixel in the bottom right corner.
So a dog leash implies a dog nearby.
Exactly. It understands the global relationships. And what's fascinating here is it uses that global understanding to power its key innovation.
Yeah.
Object query.
Object queries.
Yes. Instead of a grid or anchor boxes, DETR learns a fixed number of these queries. Let's say it has a hard limit of 100 queries. Think of them like sending 100 independent scouts out into a landscape.
I really like the scout analogy.
These 100 scouts don't talk to each other while they are searching. They just use that cross-attention mechanism to survey the whole scene, and then they all report back simultaneously. Scout number 4 finds a car. Scout number 12 finds a person.
And many of the scouts just come back empty-handed and output a no-object class.
Precisely.
But wait, if these 100 scouts are completely independent and not talking to each other, how do we avoid that overlapping mess we talked about earlier? If there is no NMS algorithm to prune the duplicates, what stops 50 scouts from all throwing bounding boxes around the exact same red car?
This is where the mathematical elegance of DETR really shines, and it happens entirely during the training phase. They use a technique called bipartite matching, specifically utilizing something known as the Hungarian algorithm.
Bipartite matching sounds heavy. How does that actually force the scouts to behave?
Think of the Hungarian algorithm like an incredibly strict, omniscient boss reviewing the 100 scouts at the end of the workday. Bipartite matching basically means drawing a one-to-one line between two sets of data, the set of ground truth objects in the image and the set of the scout's predictions.
Okay.
The boss's rule is absolute. Every real object gets assigned exactly one scout, no more, no less.
So if 3 scouts proudly come back to the boss and report the exact same red car,
the boss heavily docks their pay. Mathematically, the algorithm enforces a massive loss penalty. Over millions of training cycles, the scouts learn to coordinate implicitly. They learn to spread out.
As brilliance.
If the network senses that one query is already locked onto the red car, the other queries learn to look away and find the street lamp instead. It forces the model to learn a one-to-one mapping naturally. It's a mathematically pure way to solve the duplicate problem without writing a messy post-processing script to delete boxes.
It's a beautiful paradigm shift. I mean,
Oh,
it wasn't the fastest model out of the gate, and the notes mentioned it took incredibly long to train, but it proved you could build a clean end-to-end detection system without all the manual engineering hacks.
it opened a completely new door for research.
So what does this all mean? We have explored this wild evolution. We have YOLO with its rigid grids, faster RCNN with its tailored anchor boxes, DETR with its cross-attention scouts. If you are listening to this and you actually need to deploy software in the real world, how do you measure which of these wildly different architectures is actually best for your specific application?
The industry relies on a notoriously strict metric called MAP, or mean average precision. And it is punishing because you're grading the model on two distinct axes simultaneously.
Did it correctly classify the object? And did it draw the bounding box in precisely the right mathematical location?
Exactly. The ultimate developer headache.
It truly is. The gold standard benchmark dataset is called COCO. And COCO doesn't just ask if your model found the cat.
Yeah.
It evaluates the model across multiple, incredibly tight intersection over union thresholds.
Yeah, you can build a cutting-edge model that successfully identifies a cat, but if your bounding box is just 2 pixels too tight and clips the cat's ear, CocoGo grades you as if you failed completely.
It also fundamentally separates the scores for small, medium, and large objects, right?
It does. Because, as we saw with YOLO, finding a tiny bird against a complex background is a radically different engineering challenge than finding a massive truck taking up the foreground.
And those strict metrics directly dictate how these models map to specific industries. Take autonomous driving. If you're building the sensor fusion pipeline for a self-driving car, real-time speed is your absolute god.
You need it.
You're reaching for optimized YOLO variants or highly efficient DETR models because you desperately need those 60-plus frames per second to survive on the highway.
Conversely, look at the medical field. If you're designing software to detect malignant tumors in CT scans, the processing speed is a secondary concern. The cost of a false negative missing a real tumor is catastrophic.
Right.
So, you're much more likely to deploy a highly accurate two-stage detector, perhaps something in the faster RCNN family, where pure precision is heavily prioritized over a few milliseconds of latency.
And then you have retail analytics monitoring store shelves, counting foot traffic. There, your main constraint is hardware. You need lightweight, highly compressed models that can run directly on the edge, right on the ceiling security cameras themselves.
Without needing to route heavy video feeds back to a massive, expensive server farm.
It is deeply satisfying to see how specialized the architectures have become, driven entirely by the unforgiving constraints of the real world.
It really is.
Let's step back and look at the whole arc we've covered today. In 2014, engineers were popping champagne because a brute force memory-hogging experiment managed to process one single image in 47 seconds on a boiling hot GPU. And just a few years later, through sheer architectural ingenuity, that exact same computational task became an invisible, real-time utility embedded in the phones in our pockets and the cars in our driveways.
It really is the ultimate trajectory of deep learning. Raw academic ideas solidifying into engineering, engineering stabilizing into infrastructure, and infrastructure just vanishing into the fabric of everyday life.
But as we wrap up this deep dive, I want to leave you with a lingering engineering challenge. We have spent this entire time talking about how to draw the perfect box around an object. But think about what a bounding box actually is.
Right.
If you draw a box around a person standing in a room, you aren't just capturing the person. The corners of that box are capturing the wall behind them, the chair next to them, the floor beneath their feet. If our ultimate goal is for machines to truly, deeply understand the visual reality of our world, isn't a box just a remarkably crude approximation?
That is the frontier. What happens when boxes are no longer good enough?
Think about the computational leap required for a model to trace the exact pixel-perfect outline of an object instead. A mask that perfectly hugs the contours of a hand or a leaf. Where does the object truly end and the rest of the world begin? Something for you to mull over. Thanks for joining us on this deep dive. See you next time.